So now we will study about the concepts of quantum numbers. Quantum numbers were given to define the location of shells, the shape of orbitals, and for many uses related to atoms and electrons. So there are four types of quantum numbers. The first of them is principal quantum number. Principal quantum number. Second is azimuthal quantum number. Third is magnetic quantum number. And fourth is spin quantum number. So we'll study them. First is principal quantum number. Principal quantum number. So this was given by Bohr, and it represents the size and energy of a shell in which the electron belongs. So as we have studied in atomic number, that radius is given by 0.529 times n square upon z angstroms. So in this, n is the principal quantum number. So if you plug in the value of n and you know the species for which we are calculating the radius, so you know the atomic number. If you plug in all the values, you get the value of r. For energy of an electron, we have this formula 13.6 times z square upon n square electron volt per atom. So if you put the value of n in this formula, you get the value of energy. Similarly, mvr is equals to nh upon 2 pi. This was given by Bohr, the quantization of angular momentum. In this n is the principal quantum number. So you can see the principal quantum number is of much significance. Now, the value of n can vary from 1 to infinity, but for the elements that have been discovered so far, the value of n that are taken are generally from 1 to 7 for the elements that have been found so far. This was the the principal quantum number. So if we have the K shell, if we have the L, M and N, I'll discuss for 4 shells. The value of principal quantum number is 1, 2, 3 and 4, and the maximum number of electrons are 2, 8, 18, 32. I'll tell you how the maximum number of electrons are 2, 8, 18 and 32. Now, second is azimuthal quantum number. Azimuthal, or we can call it angular quantum number, or we can call secondary quantum number, or subsidiary quantum number. So these are the 4 names that are given to the same quantum number. So this represents the shape of the subshell and the orbital. Now this represents shape of subshell and orbital. Now I'll tell you how. I'll first tell you the value of L can vary from 0 to n minus 1. If n is equals to 1, so the value of L can be 0. If n is equals to 2, L can be 0 or 1. N is equals to 3, L can be 0, 1, 2. So this depends on the principal quantum number. Now L is required for the energy of the subshell, energy of the shell. Now how? Energy depends on n plus n plus L rule. This is given as the n plus L rule. So if I have 1s and if I have 2s, so in this case n plus L is 1, and in this case n plus L is 2. So 2s will be at a higher energy as compared to 1s. Now what in the case in which the n plus L is same? For example, if we have if we have 3s and 2p, in this case n plus L is 3, in this case n plus L is again 3. So in these comparisons, the higher energy is of the shell which has greater principal quantum number. So 3s will have a higher energy than 2p. So the significance of L was for energy also. Now I'll give you the shape. For s orbital, s azimuthal quantum number, the shape is spherical. For p, that is L is equals to 0, L is equals to 1, it is dumbbell shaped. For L is equals to 2, that is D, it is double dumbbell. And for L is equals to 3, that is F orbital, it has a complex shape. It has an electron density ring around it, so it is a very complex shape. Now the third type of quantum number is magnetic quantum number. So magnetic quantum number was introduced by Zeeman. So we have studied the Zeeman effect, that is the deflection of spectrum in when they are kept in magnetic field. So this was given by Zeeman to explain the splitting of lines in the magnetic field. Now magnetic quantum number determines the orientation of orbitals in space and is denoted by m. So azimuthal quantum number was denoted by L, magnetic quantum number is denoted by S, and it defines the orientations of orbitals in space. Now the value of m are from minus L to plus L. Now if L is equals to 0, m can be 0. L is equals to 1, m is minus 1, 0, 1, and so on. Now for D subshell. For D, L is equals to 2, so m is minus 2, minus 1, 0, 1, 2. So we can see from here that m is equals to 2L plus 1. If we want a formula for this, we get m is equals to 2L plus 1, in which L is the azimuthal quantum number and m is the magnetic quantum number. Now the values that m can take are only integral values. Now an orbital is defined in a block, as a block. So we have one s orbital is 1. P subshell has 3 orbitals, 1, 2 and 3. D has 5 orbitals, 1, 2, 3, 4, 5, and F has 7. How? For S, L is equals to 0, so M is 1. For P, L is equals to 1, so m is 3. And I have told you, or the m defines the orientation of orbitals, so the value of m gives the number of blocks that we draw for a particular orbital. Now this block, one block can contain a maximum of 2 electrons. So if we have a p subshell, p has 3 orbitals and each orbital can carry 2 electrons, so we have a total of 6 electrons. So m was given by 2L plus 1. So the number of electrons would be given by twice of m, that is twice of 2L plus 1, that is 4L plus 2. So now you can see that I told you the number of electrons in the following shells, that is n 1, 2, 3, 4 was 2, 8, 18 and 32. So from here, if n is equals to 1, that is K shell, n is equals to 1, so L has to be 0, m has to be 1, so it can contain 2 electrons. N is equals to 2, L has 0 or 1. So for L 0, 1, we use the formula 4L plus 2. So 4L plus 2, for L is equals to 0, it comes out to be 2, and for L is equals to 1, it comes out to be 6. So 2 plus 6 is 8. So you can get the values by putting in the values of L. Now shape of the s orbital, as I have told you, is spherical. So this is an s orbital, this is an electron, these are the shells. If we take the probability density of finding an electron maximum here, so this would be a spherical node. Same in the case of p orbitals, these are in the shape of dumbbell, so we'll draw them in 3-dimensional space. So these are the shapes of p orbitals. This is the negative and this is the positive shape. So if I draw all the 3 p orbitals we get something like this. I could not draw the figure, but we have the p orbital. Now d orbital is complex than a p orbital because it has a, I told you, a ring in between. Now if this is the one shape, this is the second shape, we have a ring in between this. So these are the various shapes of these orbitals, and d has 5 orbitals. 1 2 3 4 5. So these are given by dz square, dxy, dxz, dx square minus y square, and dxy yz. So these are the 5 shapes, and these zx represents the d orbital along the zx plane, yz along the yz plane. So this was about the magnetic quantum number. The fourth type of quantum number is spin quantum number. Spin quantum number. Now it represents the direction in which the electron spins. So according to a theory that we will be studying in the next lecture, it was said that in an orbital the electron cannot have the same quantum numbers. So if an electron rotates clockwise, the other electron has to rotate anti-clockwise. So the rotation is given by a spin quantum number. Now for clockwise spin it is plus half, and for anti-clockwise spin it is minus half. So the value of s is plus or minus half. Now if we have to calculate the spin angular momentum, we have the value under root of s into s plus 1 h upon 2 pi. H is the Planck's constant, so we also by h dash. So the value of h dash is equals to h upon 2 pi.